Hello guys, and welcome again to my channel. This is definitely going to be episode 5, and episode 5 is going to be line spectrum and Bohr's orbit of hydrogenic atoms. So this is official 5th episode. How are you liking the channel so far? I'm hoping you're enjoying it. Personally, the content in it has been life-changing and inspirational to me. It's opened my eyes to chemistry. Now, let's get right into it, shall we? So, hydrogenic atoms can be defined as atoms that contain only a single electron, right? For example, a helium atom which has a positive charge, a lithium atom which has 2 positive charges, and a beryllium atom that has 3 positive charges. So the length spectrum of these atoms can be calculated using this equation. V with a stanza above it, Ni into which reacts into Nf is equals to Crz to the power of 2 into brackets 1 over Ni squared minus 1 over Nf squared into brackets. Now that's the equation which we use to calculate these length spectrum of these atoms, right? So this equation, let me explain it further. This equation, where Ni is considered the grounded state energy level, Nf is considered the excited state energy level, Vni minus Nf, like V Ni minus Nf with a capital V, is considered frequency of the Ni into Nf transition in centimeters raised to power -1. Right? So Z, which our Z for today has a line crossed across it, is the atomic number of the hydrogenic atom. Okay? The atomic number of the hydrogenic atom. And then the Cr is the Rydberg constant, R, and the Rydberg constant is 109,677.57 centimeters raised to power -1. This formula gives you the ionization energy, right? What a formula. This is the formula we use to calculate the whole topic, right? Capital V with a stanza, Ni into which reacts into Nf is equals to Cr Z raised to power 2 into brackets 1 over Ni squared minus 1 over Nf squared into brackets. A powerful equation, if you ask me. The equation of our lives, if you think about it, right? So let's continue. The ionization energy can be determined. We can determine the ionization energy of a hydrogenic atom by setting Nf into infinity. The electron distance becomes practically infinite, right? Nf becomes practically infinite, right? Nf arrow infinity. So the equation for Nf going to infinity is a capital V stanza, small Ni, the arrow Nf is equals to Cr7 squared into brackets 1 over Ni squared minus 1 over infinity, close the bracket, is equals to Cr into brackets Z over Ni, close the bracket, squared. Now, this equation for Nf turning to infinity is because of setting Nf to infinity. We get this equation for hydrogen in its ground state. It's for its ground state, right? The hydrogen, the atom into its ground state. So V ionization is equals to 10109,677.57 centimeter negative 1 into brackets 1 over 2, 1 raised to power 2 over 1 raised to power 2, close the bracket, is equals to 1099677.57 centimeter negative 1. So technically the ionization is equals to 1099677.57 centimeter squared, the ionization. Let's continue. By now I'm guessing you're floating, but do not worry, it's okay, it is okay. Just try and keep up and learn, okay? So the energy associated with this frequency can be calculated in, how am I going to explain this? Well, it's a new symbol for us, but I bet you've seen it before. It looks like this, right? You know these symbols, right? You've seen it before. Is equals to 1 over the V with a stanza is equals to 1 over 1096677.57 centimeter into bracket 1 meter over 100 centimeter, close the bracket, is equals to 9.117 times 10 raised to power negative 8 meters. So that's how the energy with this frequency can be calculated. So if we go into the results of this equation, we get E is equals to H into bracket C over that one, close the bracket, is equals to into bracket 6.626 times 10 raised to power negative 34 joules, close the bracket, into brackets again another bracket 3.00 times 10 raised to power 8 m over s, like mels per second, over 9.1117 times 10 minus 8 meters, close the bracket, is equals to 2.18 times 10 negative times 10 raised to power negative 18 joules. Now here is why our chemistry is coming to a standstill. The experts who actually define these calculations usually have a drawing board to actually show you these equations while they teach you, right? So in my channel I'm just going to give you these equations basically on a layman's term so that you can understand these equations and just get it, right? Because that's the vision I have for this channel. So E ionization is equals to 13.6 CV. In the end, when you calculate it with this equation, it equals to 13.6 as we have seen. You'll get it. You can just refer. If you're finding the class to be a bit challenging for you to get it, you can just refer. So let's go on. The Bohr orbits. Let's now study the Bohr orbits. Now the Bohr orbits is the distance between the nucleus and the electron at its energy level n for hydrogenic atoms only. The Bohr orbits. So this is the formula for the Bohr orbit. Rn is equals to a small o n squared over z. That's stanza in between, right? So Rn is radius of the Bohr orbit at n. AO is the Bohr radius, which is 5.29 times 10 raised power negative 11 meters, and Z is the atomic number of the hydrogenic atom. Now, so far, I can just imagine you're finding it hard to catch stuff, but there was a lot of equations going to this class, a lot of new symbols we had to tackle. We've seen the Z, the that one, the V, but they are all studied in this chapter of chemistry. So you just hold on to your heart and hope that you'll get like a great vision. The sole purpose of this episode and this channel is to like broaden your horizon. So I'll just go through it, and if you want to refer to it to get better knowledge and see these equations, you can just go online on YouTube and you'll just catch them, right? So let's go on. So for our first sample problem, we get for a hydrogenic atom, He, helium, with a positive charge. So we are going to use Z is equals to 2, like we're bracketing that. So calculate the wavelength of the first three lines when Ni is equals to 1. So we're going to use helium for our first sample problem, and we're going to calculate the wavelength for the first three lines when Ni is equals to 1. Okay, so the formula we're going to use is V small ni into Nf is equals to Z with a helium raised to power 2 Cr, open the bracket, 1 over Ni2 minus 1 over Nf squared, and then close the bracket. So yeah, so let's start the calculations, shall we? V1, the first one is going into 2, and then it's equals to 2 raised to power 2 into brackets 109,677.57 centimeter raised to power negative 1. You close the bracket, open the bracket again, 1 over 1 squared minus 1 over 2 squared, close the bracket, is equals to 329,032.71 centimeter raised to power negative 1. Close the bracket, open the bracket, 30.392 meter nm, close the bracket. So that's the first line. We consider that the first wavelength we've been calculating. The second one is V with the stanza 1 minus 3 is equals to 2 raised to power 2 109,677.57 centimeter raised to power negative 1. Close the bracket, and the bracket again, 1 over 1 squared minus 1 over 3 squared, close the bracket, is equals to 389,964.69 centimeter negative 1. 25.64 nm into brackets. That's the second one. I'm gonna finish this stuff. So the third line is V1 into 4 is equals to 2 raised to power 2 to brackets 109,677.57 centimeter negative 1. Close the bracket, open the bracket again, 1 over 1 squared minus 1 over 4 squared, close the bracket, is equals to 4,11290.89 centimeter raised to power negative 1, close the bracket, to 4.31 nm, close the bracket. So that was helium, the wavelength, the lines in the wavelength. We've calculated them. We've seen them and the results. We could go through them again if you want to, but we choose not to. Yeah, let's calculate the second sample problem. Let's calculate the radius of Bohr orbit of these excited states. Now the formula is going to be Rn is equals to AO into brackets n squared over Z helium, close the bracket, 1.00 A is equals to 1 times 10 minus raised to power negative 10 m, which A is the angstrom. Let's do the calculations then. I'll be a bit more clearer. You'll understand the other calculations with these ones. So R squared, R is to power 2 from below, is equals to 5.29 times 10 raised to power negative 11 m, close the bracket, into brackets, it's 2 squared over 2, close the bracket. This gives you the answer is 1.058 times 10 raised to power negative 10 m, which as a result is 10.058 angstrom. The second one is R3, is equals to 5.29 times 10 minus 11 raised to power negative 11 meters, close the bracket, into brackets, 3 squared over 2, close the bracket, is equals to 2.381 times 10 raised to power negative 10 m, which results to 2.381 angstrom. The next one is R4 is equals to 5.29 times 10 raised to power negative 11 meters, close the bracket, into brackets, 4 squared over 2, close the brackets, is equals to 4.232 times 10 minus raised to power negative 10 m, which gives you 4.232 angstrom. Yeah, those are the equations to calculate them. This episode wasn't really that clear, but we've doubled in line spectrum and Bohr orbits of hydrogenic atoms. So this class was a bit challenging if you think about it. Yeah, that was the most challenging experience so far. The calculations ended up giving us a hard time understanding the class. It was more practical. It was more numeric. Let's say numeric. But if you did get these equations and all these calculations, then you will understand that this topic was actually fascinating. The hydrogenic atoms, which we've defined and stated, we've seen the formulas, we've defined all these new terms that we've experienced, the ionization energy, the formula to calculate it. We've seen so many things, we've seen so much, the Bohr orbits, the sample problems. It's been a crazy ride. I hope you've enjoyed it. Let's not be hard on this class. What I would recommend is to actually think critically about not what we have seen, but try to understand what we have experienced. This has been groundbreaking chemistry. defined by one of our greatest graduates. So this topic should be brilliant to a wise individual, right? If you're a critical thinker, then you would know what you have consumed was groundbreaking chemistry, right? So don't be consumed by errors and datas. Just try and learn, right? Sindio. Now that's all for today, folks. Until we see you again, Austin.